say loudly. I'm not, for example, you are what you are saying. I'm not able to hear. So sir will be here from USA. Okay. So just loud.
Okay, so in the last class, we had discussed mostly on finding factors and finding the least common multiple. Remember LCM? So remember the way that we find the LCM, least common multiple, is by out, listing the first few multiples, right? Listing the first, so yeah, listing the first few multiples of the both numbers we are comparing, and then we want to find what is common in between them. So today, to finish off this topic, we will learn about HCF, which is the second part, highest common factor, and we will learn about rational and irrational numbers. So the HCF, highest common factor, is the greatest factor shared by two or more numbers. So we find it in a way similar to the least common multiple. So
Rishi sir, just your speech is some left side corner is not visible. Just reduce your resumes.
sorry, reduce what?
So left for us, left side corner is not visible. Proper text is not viewing.
The text.
Just reduce your resume.
Mm, you mean you are not able to see this presentation?
Yeah, few some is not viewing properly. Left side for us,
For you?
not
Okay.
viewing properly. Few text are missing.
Is it visible now or still it is cut off?
No, still like that only.
Okay. Let me try to reshare.
Yeah, now it is blue.
Now it's good?
Yes.
Okay. So continuing on highest common factor. So we'll find it in the same way as we do for the multiples. We will list the factors for each number we want to compare, and we will choose the largest factor that is common with each set. And this will be our highest common factor. So now let's see some examples. So here we want to find the highest common factor of 18 and 24. So we'll start by finding the factors for 18, then we'll find the factors for 24, and we will compare.
How to do that?
So for finding the factors, which is the first number we always start with? Does anyone remember? To find the factors, we start with which number? Oh, anyone knows?
Yes, anybody knows about this? You can say answer. Which factors first? Which number of factors we are find first?
Correct. So we start with 1. Then we will continue with 2. So is 2 a factor of 18? So 2 is a So 2 is a factor, 3 is also a factor. Now we'll move to 4. Is 4 a factor? No. And what about 5? And what about 6? But 6 times 3 equals 18, right? So we will draw our line and start going back up. So 2 times what is equal to 18? 9, and 1 times 18. Okay, so good. This is our factors list for 18. Now we will do it for 24. So we'll start with 1, 2, 3, 6, right? 8, and 24. So now we want to find the biggest number that is in both of the factored lists. So can anyone find which number that would be? Correct. 6 is the factor in both sets, and it's the greatest factor. So the highest common factor between 18 and 24 is 6. So everyone understands highest common factor, how we can find it? Good. So we'll just do one more example very quickly. So you want to do 30 and 45. So we'll start with 30. 1, 5, right? 6,
10 already. 30.
good job. Now for 45, we'll do 1, 3, right? 5, 9, 15, right? 45. So highest common factor is what? Good. So we have learned how to find highest common factor and how to find least common multiple, but we need to understand when to use each of these, right? So we use least common multiple when we have events repeating and we need them to occur together. And we use highest common factor when we want to divide into equal groups. So maybe you don't understand yet, but we will see some examples that demonstrate when to use highest common factor and when to use least common multiple. So let's see one example. So 2 school bells ring every 6 and 8 minutes. After how many minutes do they ring at the same time? So do we need to use LCM or HCF? So why would we use HCF? Think about it carefully one more time.
You can say in English. So it's a can't understand in Telugu. Okay. So you can say what are you thinking? You can say how you can represent. There is no. Okay. So what are you thinking? You can say. Who said? Yeah, you can speak. Speak loudly. Just
Anyone knows if we should use LCM or if we should use HCF for this kind of question?
does anybody knows about it? LCM or HCM? LCM. So this is asking why we should take for LCM. We should find the multiples of 6 and 8. So we use LCM.
So you said the correct explanation. So we need to find the multiples of 6 and 8, and this will give us our LCM, which is when they will ring at the same time. So for example, let's do the multiples of 6. So we start with times 1, right? So we'll do 6 times 1 is 6. What is the next multiple? 12.
18, 24, 30, 36.
Okay, so this should be good. Now we'll do multiples of 8.
16, 24, 32, 40, 48.
So we see that 24 is common between the two sets, right? So 24 is the least common multiple. So what this means is the first bell will ring at 6 minutes, it will ring at 12 minutes, it will ring at 18 minutes, 24 minutes, 30 minutes, 36 minutes, right? But the second bell will ring at 8 minutes, so they will not ring at the same time. It'll ring at 16 minutes, so it'll not ring at the same time. However, it will ring at 24 minutes, and so will the first bell. So both bells will ring at 24 minutes. So this is one example of where we use LCM. So has everyone understood? Is there any doubts? No?
Yes, sir. How to identify this is LCM, video LCM?
Sorry, could you repeat one more time?
How do we identify video LCM?
Sorry, I'm not able to hear the question.
Our doubt is how we do identify when we have to take LCM and HCM.
Yeah. So we'll see now an example of when we have to use HCF. So this one that we have just done is an example of LCM. So is anyone able to tell me why we have to use LCM for this question and not HCF?
I will know the
So remember the scenarios here. So we use LCM when events repeat and need to occur together. So remember the problem we just did, the bells are ringing and they need to ring at the same time. So if we go back to this definition, the event is ringing and we need two bells to ring at the same time. So that's why we need to find the least common multiple of the two bells to see when they will ring at the same time. So maybe it'll be a little bit easier to understand once we see this example here. So I have 24 red balls and 36 blue balls. How many groups can I make where the number of red balls and blue balls is the same for each group? So for this question, will we use HCF or will we use LCM?
LCM.
So HCF is correct. So remember, from our definition, we use HCF when dividing into equal groups. So here it's clearly a division problem. We want to split the 24 red balls and the 36 blue balls into groups. So we want to divide them into groups. So we'll start by finding the highest common factor of 24 and 36. So let's do 24 first. So we have 1, 2,
3,
They are
4, 6, 8, 12, 24. 1, 2, 3, 4, 6, 9, 12, 16,
into 2 times.
Good. So, what is the highest common factor of these two numbers?
12.
So, this means we can make 12 equal groups of red and blue balls. So, how many red balls will be in each group, and how many blue balls will be in each group? Can someone tell me? So, if we have 12 groups of equal amounts of blue balls and then of equal red balls, how many red balls will be in each group, and how many blue balls will be in each group? This one is just simple division. So I think I heard someone say 2 red balls. That is correct, because 24 red balls total into 12 groups is 2 balls per group, right? So we'll have how many blue balls in each group? 3, right? And we could have got that from our factors list. See, we have 12 and 2, and we have 12 and 3. So we'll have 3 blue balls and 2 red balls in each group. So again, we use LCM when events repeat and they need to occur together. So we need to find the multiples. But we use HCF when we are dividing into groups equally. So we need to find the factors. So everyone is understanding when we use HCF and when we use LCM? Good. And if you have any doubts, then you can rewatch the video that we'll upload to YouTube, so you can recap if you need. So now we'll finish this topic's lesson with the last 2 categories of numbers. So remember, we learned natural numbers, we learned whole numbers, and we learned integers, right? Now we will learn about rational numbers. So rational numbers include fractions and decimals. Have you all have heard about fractions, correct? Good. So rational numbers can be written in the form of P over Q. And these are any 2 numbers. So just imagine any 2 numbers in place of P and Q. So there are 2 requirements to have a rational number. The first one is that the 2 numbers in our fraction both have to be integers. And the second requirement is that Q cannot be 0. So P can be 0, the top number can be 0, but the bottom number cannot. So for example, 3 over 4 is an example of a rational number because 3 is an integer, correct? And 4 is also an integer. Integers themselves also are rational, right? 5 is an integer, correct? But 5 can be written as 5 over 1, which is the P over Q form. That means 5 itself is a rational number. Lastly, in terms of decimals, terminating decimals, so decimals that end, are rational, and repeating decimals also are rational. So terminating decimal is something like 0.25. Repeating decimal is something like 0.66666 and so on. So just to recap, rational numbers are numbers that can be written in the form P over Q. So fractions are rational. Integers themselves are rational. Terminating decimals are rational, and repeating decimals also are rational. So, does everyone understand, or is there any doubts? Was someone asking a question? I think there is some lag. I'm not able to hear properly the question.
Sir, she's asking one more time. You can explain for the rational numbers.
One more time, explain rational numbers.
Yeah. She's asking that one.
Sure. Okay. So you all are familiar with fractions. You've at least heard of fractions. So rational numbers are a type of numbers that can be written as a fraction. See, this form here, P over Q, is a fraction. So in order for a number to be a rational number, the numerator, so the top of the fraction, and the bottom of the fraction, P and Q, both must be integers. Remember, integers are, for example, -1, -2, 0, 3, 5, and so on, correct? And the second requirement is that Q, so the bottom part of the fraction, cannot be 0. So these are the two requirements that we need for rational numbers. So these are the 4 types of ways we can express rational numbers. So any fraction is a rational number. For example, 3 over 4 is rational because the top is an integer and the bottom also is an integer. 2 over 5, for example, is rational. 7 over 8 is rational. So all of these fractions with integers on the top and bottom are all rational. So integers themselves are rational. So if we see the number 5, it is rational. Any integer is rational. And the reason for it is because 5 can be written as a fraction. So 5 over 1 is how we represent the number 5 or any integer as a fraction. So it is rational. Decimals also are rational numbers. So terminating decimals, so decimals that end, are rational. So 0.25, for example, 0.75, 0.18. All of these decimals are rational. And if you're not comfortable with decimals yet, then don't worry, we'll cover that in the next couple topics. And repeating decimals, so decimals that don't end, also are rational. For example, 0.1 repeating, or 0.6 repeating. These also are rational numbers. So is everyone understanding now how we can define rational numbers? Good. So here's just some examples. So -6 is an integer, so it is rational. 0.7975 is, remember, a terminating decimal, so it is rational. 0.33333 repeating is also rational. And 2.5 is a terminating decimal, so it is also rational. So any numbers like these that can be written as P over Q form is rational. So on the number line, remember, the whole number line is integers, whole numbers starting from 0, and natural numbers starting from 1. So rational numbers is everything you see in between. So for example, here's 1, 2, 3, 4. Here might be 1 over 2. Here might be 3 over 2. Sorry, 3 and 1/2, so 7 over 2, for example. So any numbers that we see in between are rational numbers. However, integers only fall on the lines, whole numbers only fall on the lines, and natural numbers fall on the lines only. Anything in between will be a rational number. So everyone is understanding the number line representation. So the last category of numbers are irrational numbers. So these are numbers that cannot be written in the P over Q form. So irrational numbers are decimals, specifically, that do not terminate, nor do they repeat. So they don't terminate and they don't repeat either. So some examples is something you see here. Here we just see a bunch of random numbers and it keeps going, but it does not repeat either. So for example, a repeating decimal would be like 0.66666. There's a pattern, right? 6 is repeating every time. But here, there is no pattern. It's just a bunch of random decimals. So this would be an irrational number. Another common example is the square root of 2. So remember, 2 is not a perfect square. So it's a decimal that does not terminate and it does not repeat. And another example is pi, which is 3.14159 and so on. So this number as well is irrational. So does everyone understand on irrational numbers?
Yes.
Good. So we've covered all the numbers in the number system so far: natural numbers, whole numbers, integers, rational numbers, and irrational numbers. So that is the end of topics 1 to 3. And you can recap if you have any doubts with the YouTube videos. But do we have time, more time for today's class, or is it time to go?
It's time to close.
Time to close. Okay. So we will continue the next few topics. So that's topics 4 to 7 we'll discuss in the next class. So hopefully you've all have understood. But if you have any doubts, you can watch the videos afterwards, recap. Um, but hopefully you guys learned something today, and thank you for having me as always.
Thank you.